Hi all. So we're going to talk about this idea of complexity analysis. Basically, how computer scientists will evaluate the efficiency and the complexity of algorithms. Okay, this kind of came up actually earlier when you were dealing with, for instance, the array dupes discussion, and people were talking about that their implementations were, quote, inefficient, and things of that nature. So it's kind of important to kind of talk about how it is that we actually do evaluate this notion of whether something is inefficient or efficient and so forth. Okay, so let's start by looking at some code. So what I have here, I have this code here, and again, you'll be able to, it'll be linked, so you'll be able to get this. But basically, what I have, so here's main. Notice I just define a variable that is the number of numbers that I want. Then I create a vector of that size. Okay, so I do nums and then num size. Now, one note about this, you'll notice I'm not using the universal initialization syntax, right? That is, a lot of times we do this. And for the most part, we can get away with that. The problem is what this would do, this would actually create a vector of size 1, and the only value that is in it is basically the number 10. On the other hand, this will ensure that the vector constructor is called. We're calling the constructor that takes an integer, basically saying that's the initial size. Okay, so we create the vector of that particular size. And then what we're going to do is we're just going to generate a bunch of random numbers. Okay, so that's what there's the generate function. That's from that actually is in the functional header. And notice it's calling it basically, so the idea is it's going to go from the beginning of nums to the end of nums and call randFun. Okay, so what is randFun? Well, it's a binding of this function, randin. Okay, randin is defined in helpers, and basically all it does is, as you can see, so it returns a random number between low and high inclusive. Okay? So notice that takes two parameters, a low and a high, and the idea, if you take a look at the documentation for generate, you'll see that that it actually takes a function that doesn't take any parameters, right? So what we're doing with bind is we're saying, okay, give us a version of randin that where the first thing is bound to min number and the second thing is bound to max number. Now, where are these coming from? They are global constants. Okay, so our min number is 1 and our max number is 100. I could make these whatever I wanted. It could be 5 and 20. It could be negative 13 and then positive 17. I mean, whatever. That doesn't really matter per se. Just we want some random numbers. Okay, so we generate some random numbers, and here I'm actually going to print out the numbers. Now I am printing out. You'll notice actually I am using the put to operator with the vector. That's not built into C++. Again, in the helpers in helpers.h, there's a templated function for printing this out. But just to kind of give you an idea of what this looks like and what this actually does, right? So there it is. So there's nums. There are 10 random numbers between 1 and 100 inclusive, right? And every time I run this, I should have different random numbers. Okay, that's all that code is doing. Okay, so it's generating an array of a particular size for us with some random numbers in it. Okay. Now, why am I doing this? Well, basically because I want to talk about an algorithm, and I want to talk about things, namely the efficiency of particular algorithms and so forth. Okay, so we're going to do that. Basically, what we want is the algorithm that we're going to talk about is simple linear search, right? Which I have actually implemented right here. So search is an unsorted vector for the specified number, right? So we pass in the vector by reference, we pass in the number that we're looking for, And since it's unsorted, the best that we can do, we simply start at the first number, the index of the first number, and then just ask, okay, is this the number we're looking for, right? So let's say we were looking for the number 1000 in this list. We'd come over here and we'd say, okay, is 92 the number that we're looking for? No. Then we'd say, is 22 the number we're looking for? No. Is 39 the number we're looking for? No, etc., all the way down to the end. And finally, if we don't find it, the for loop ends and we return -1. If we happen to be looking for a number that was in here, let's say I was looking for the number 18, right? I'd come here and say, no, that's not it, that's not it, that's not it. I find 18, so I'm going to return the index of that particular number, right? So in that case, it's 0, 1, 2, 3. Yeah, so that's what we would get. Okay, and just to prove that that this works and so forth, though, we can actually do a couple of different things. So let me make kind of a copy of that real quick. I don't actually need this one. And, I can show you. So, for instance, if I have these particular numbers in here directly, if we, then we can say, for instance, cout search nums and 18, and cout search and nums, and let's do 92, right, the one right at the beginning, just so we can see that, and maybe one more, search nums, and let's do 1000. Okay, so few different things. All right, so if we take a look, so there's our numbers, right? Notice 0, 1, 2, 3, that's where 18 is, right? Of course, 92 is at the first position, and the number 1000 does not occur in our vector. All right. So showing, yes, our search function does work the way that it in fact should. All right, so once since we have that, now we can talk about efficiency, how and in fact how we actually would deal with or talk about this idea of efficiency. Okay, so I'm going to go back to kind of generating this, and one way of doing this, one way that sometimes people think about the efficiency of code is by using a stopwatch. Right? So that is basically what we can do is we can sort of start our stopwatch as soon as a call to search happens, and then stop the stopwatch when it ends, and compare those two times, and then we have an idea of how fast that particular function runs. Okay? In fact, I've actually built a function for doing that, right? So I have this function here called timed search. And notice, so it's going to time how long in milliseconds it'll take to search for a number that isn't in nums. Okay, so here's how we actually sort of start the stopwatch, so to speak. Really, what we're doing is we're just getting the time at that particular instance. Then notice, we call search, and I'm going to search for a random number between whatever maximum number is plus 1 and integer max. So basically I'm just guaranteeing that it's a number that isn't in the array. Okay, when search returns, then basically again we take another look at the clock and we compute we figure out what the difference is. We do a stop minus a start, and that gives us basically a difference. And then we can convert that into whatever format we want. So for instance, if I want milliseconds, I can do it this way. If I wanted other kind of time frames, seconds and so forth, there are other modifiers that we can use. But let's start playing around with this. Let's see kind of what we can get with this. Okay, so I have my 10 numbers, and there we are generating it. I'm not even going to bother printing these out anymore, since you now know kind of what that does. So I'm just going to do a cout, and we'll do timed search, and we'll pass along numbers just like so, and and L. Okay, and so we do know it does say that it was going to be in milliseconds, so let's take a look at that, right? And there it is, 0 milliseconds. Now, did it really take 0 milliseconds? No, it actually took less than 1 millisecond, which is why we're not actually getting anything. I mean, to search a collection of size 10, that's our processors are so fast that that's nothing for them. Okay, I could try actually bumping this down to nanoseconds just to see if that gives us anything. And so we run it, and again, I mean, notice it's 0 at this point. It's nanoseconds. So again, doesn't really seem to be giving us anything. Let's try bumping up the size. So let's go from 10 to 100. Okay, and again, searching an array of 100, even going through 100 elements, it takes ostensibly no time. Okay, so let's make it bigger. Right, still, we're not getting anything. Let's make it bigger still. So now we're at 10,000. Okay, still no time. Let's try 100,000. Ah, there we go. Now we're actually starting to get something. So notice we got a bunch of stuff here. We'll put in a couple of little formatters just so it is a little bit easier to view. So I'll put in the fixed formatter. That way we don't have all that extra stuff there. Okay, so that's the number of nanoseconds that it took. I got a bunch of things after the decimal point. Again, we can sort of adjust those things if we want as well by using say set precision 1. So I only want a single number after the decimal point. Okay, so there's roughly what we have for 100,000. What do we have? We have 1 million nanoseconds. Okay, so now we're actually getting to a point where we're able to test this. But some of the things that I want you to kind of notice. So there it is an even 1 million. Before I kind of had some extra stuff in there. Again, right? So I notice I have an extra 100 nanoseconds sitting around inside there. Okay. So some things about this, right? So if I increase the size, I may even begin to start to see some other differences, right? So let's see, what is this? This is 12 million nanoseconds. Now notice 16 million nanoseconds. Okay, so now actually we're probably in the range that we can switch this back to milliseconds and still see a reasonable result. Right, so there's 12. Let me take out our set precision. Okay. So 11.0006 nanoseconds, right? 13.0008 nanoseconds, 11, right? So here's the question, though. Notice, what I want you to notice is nothing's changing in my program here, right? I'm still searching a vector of the same size, in this case, a vector of size 1 million, and I'm always searching for an element that isn't in the array. But I'm getting slight differences in terms of the runtime. So that's kind of weird, right? No, it's 13 milliseconds, 11 milliseconds, 13 milliseconds again. I mean, they're kind of around the same area, but something's going on. Okay. So the issue that we have with this is, given the fact that at any given time there are different things running on my computer, this process can take a different amount of time. And that begins to kind of show some of the problems with using raw clock times to figure out the efficiency. So, for instance, if it happened to be the case that all of a sudden I'm running a whole bunch of more things on my system, then suddenly the runtime is going to peak up, right? Does that mean that suddenly the algorithm or the program is less efficient? No, it doesn't, right? What about if I take this program and I run it on a computer with a faster processor that is running fewer things? Now it's going to take less time. Again, does that mean that the algorithm suddenly or the program suddenly became more efficient? No, it didn't, right? So that's part of the issue with this, right? Part of the issue, the reason that we don't just use raw clock time, is because so many things can cause that to vary. Okay. Now, having said that, the kind of theoretical measures that we're going to look at and show, we can get the clock times to kind of reflect what is going on with that, okay? And I'll show that actually today as well, right? So let me show you a couple of different things and some different ways that we sort of look at this and so forth, okay? So first of all, if I really wanted to kind of play around and I really wanted to get better sense of how this algorithm works, we have to come up with a better idea or a better way of conceptualizing the efficiency and the complexity for a particular algorithm. Okay, and notice I'm talking about algorithms, right? So we sort of switch from this notion of the efficiency or complexity of a program to the efficiency and complexity of an algorithm, right? Why? Because the idea is what we're going to see is really when we're talking about the efficiency, it's inherent in the steps or the way that the algorithm chooses to solve the particular problem. Okay, so in computing, what we're really interested in is this idea of how does the efficiency, how does the complexity change as our input size grows. As the input size gets bigger and bigger and we say actually approaches infinity, how does that change how much longer it takes? So, if adding 1 to the size of efficiency, does that add just a couple of nanoseconds? Does that add a few seconds? Does changing it does changing it by 1 now all of a sudden mean we had a program that took maybe a half an hour and now all of a sudden it takes a week to solve that problem? Okay? So we're interested in this notion of the size and how that actually affects the overall notion of the algorithm. Okay, so let's take a look at this. Let me kind of hide that again because we don't need to be looking at that directly. So if we were going to evaluate this function, what we would take a look at is basically we'd say, okay, look at. So what this function ultimately is dependent on is the overall size, the number of numbers that we have, right? So, take a look. We have a loop that says, okay, we're going to start at the first one, and now we're going to have to look at every single element in that particular vector, right, to find out whether an element actually exists in the vector. And in the worst case, if it's not there, then we're going to look through all of the numbers in the vector to find out that, yeah, it isn't there, right? We're doing the proverbial trying to find a needle in a haystack, right? Especially, now here we have a haystack, we have 1 million numbers, and we're searching all 1 million numbers to try to find a particular number that it turns out doesn't even exist there, okay? So the idea is that basically, how many operations do we have, right? So imagine, if the size of the array was 1, Well, if we take a look at the loop, we basically we do sort of one thing. We do this comparison, and again, if it wasn't found, then basically we do nothing else, right? So we're doing a single comparison, right? So we go through, we say, okay, is that particular number the one that we're looking for? It isn't, okay, fine, and then ultimately we're going to return. So we basically have two steps, okay? If we have two elements, right, we're going to look at the first thing, say, okay, maybe that's not the one. We look at the next thing, say that's not the one, right? And then we have one more thing, again, basically returning our -1, okay? If we have three things, again, we're going to do three comparisons and then finally return -1, okay? So what we essentially say here is this algorithm is basically going to do, if there are n number of things in the algorithm, it's essentially going to perform n plus 1 operations. Okay? Right? If there are n number of elements, it does n comparisons, and then ultimately, yes, it finds out that if it is not in there, it's going to have one more operation for returning that. Okay? So n plus 1 operations is how many we're going to do. Okay. Now, here's the thing that I want you to consider. So if we're looking at this notion of n plus 1 operations, right? We oftentimes talk about this. Let me actually sort of pull up this. Okay. So our formula is n plus 1, right? Let's do it this way. So I'll say, all right, if n has some value, then n plus 1 has the following. And then let's just put in, right? So let's say 10, and then let's say 100, and let's say 1,000, and let's say 10,000, etc., right? So this is just going to be equal to plus 1. Right? So n is that, n plus 1 is that. Here's what I want you to notice. All right, again, when we're talking about asymptotic analysis, we're interested in this idea of what thing has the biggest effect, right? So in an expression like this, where we have n plus 1 operations, I mean, in the case that there were only 10 things, okay, adding 1, that's sort of an extra 10%. But notice, when there was 100, now we've only had 1%, right? And so as the number of elements gets bigger, what we end up with is that extra 1 element doesn't really matter so much. Okay? That we don't really care so much about that particular thing. So what we're saying basically is the n part of this is the dominant term, right? Basically, as n goes to infinity, the thing that largely dominates this function is the value n. Okay? All right. So don't save. Now, let's take a look. So we'll go to the book, talk about this. So computer scientists, right? We talk about this notion of, here we are, asymptotic analysis, and one of the first ways we kind of talk about this is using something called big O notation. Okay, so the formal definition is here, right? So you have these functions, f of n and g of n, right? Where n is notice, in z, so that's a positive integer. Okay, and then we can say, okay, f of n is big O of g of n if and only if there exists a real number c and positive integer n satisfying blah, 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 right? Did you glaze over just then? All right. So here's the basic idea, right? So our linear search had n plus 1 operations. You can excuse my horrible handwriting, right? So we can say that the runtime for this is proportional, right, to a function that is like so. F of n equal to n plus 1. Okay? Now, if we want to know, if we want to ask, what function, can we find some function that represents or that, or rather that bounds this overall function? Okay, that whole notion, the whole notion that we were looking at before. There we are. Okay, what this is basically saying is that when we say that f of n, right, our function, is big O of g of n, what we're saying is essentially right here that we have some other function. There's some other function that grows faster. Okay? Now again, kind of difficult to envision some of these things. So let's take a look, right? So I'm going to go over here to this Desmos thing. It's this nice little Functiongrapher that allows us to kind of view and play around with these different things. So again, we were dealing with f of n equal to n plus 1. Right? And so there that is right there. I'm actually surprised because normally it doesn't seem to want me to deal with n's and seems to generally want to deal with x's. In fact, if I do this, you'll notice it says, hey, I don't understand that. But if I do actually label it as x, there it is, right? So there's the graph for x plus 1 or n plus 1, right? Hopefully we're okay with the fact that, whether it's x or whether it's n, it's still the same function. Okay, so here is the graph for x plus 1, right? Now, let's consider. So a couple of things to look at. One, so the idea is as x, which is basically the size of our input grows, we can envision basically that the size of our input is on the x axis here, and how much time it takes is on the y value. Okay, so for instance, things like negative 1x are nonsensical for what we're talking about, right? It doesn't make sense to talk about having a negative amount of input. Also, anything that's in the negative section for the time likewise doesn't make sense, right? It took negative amount of time. Again, that's kind of weird. All right, so really what we're interested in is this quadrant here, right? So notice when x was 0, okay, it took 1 time. When x is 1, it took, right, let's see, is it there? Where is it? Probably zoom in. Yeah, so x is 1 is there, right? 1.3, it's 1.03, right? So there it is, roughly there. Okay, so we can see that this is what we refer to as a linear function, right? So the amount of time that it takes grows in sort of a one-to-one in a straight line proportion to the x's themselves. Okay, let me show you something that isn't linear. For instance, x squared. Okay. Notice this function, there's a couple of things to notice. One, in terms of its rate of growth, notice it's going to grow way faster, right? That is, by 5, okay, by 5, when our linear function is at value 6, our quadratic function is well off the scale at this point, right? But notice a couple of other things as well. Notice that there are actually a few x's here where x squared was doing better, right? You see that right in here? X squared was actually doing better up until the point of x being 1.618, okay? And so again, if we refer back to the definition, right? So they're saying, look it, okay? This holds, this idea of f being big O of something holds, okay, first of all, is there some number and a positive integer n where f of n is less than c times that thing? So let's say, so in our case right here, the c number that we're actually using is 1, right? 1 times this and 1 times that. right? So we haven't adjusted this at all. And so in that case, right, the question is there some big N, in this case 1.68, beyond which our x plus 1 is less than that other function? Yes, it is, right? And it goes on forever, right? X squared is not going to come back down, and so forth. We can, as we zoom out more and more and more, we see, yeah, x squared has rocketed to the sky, way down here, and there's x itself. So x is in fact growing slower than this function here. Okay, so what we could say is that our function, x plus 1, is big O of x squared, okay, by the definition of xo. Now, could I find other functions as well? Sure. For instance, how about x cubed? Right? So there's x cubed, and yeah, certainly x is, the function x plus 1 is actually less than that. Yeah, absolutely. Right, and we could find various orders of polynomials for this to occur. But part of the question is, since there's almost an infinite number of functions that grow faster than our function, really what we want to do is find one that does grow faster, but is pretty close to the function itself. Okay, so let me get rid of these. How about x itself? Right? So there it is. Now you might say, well, wait a minute. Okay, hold on. First of all, it's underneath there. So that's kind of weird. Right? What's going on with that? Okay, but then remember, I could, as long as there's some constant that I can multiply this by, that beyond some particular point, this is less than that, which it is, then yeah, we're good, right? And I could do 1.2, I could do 0.2, so I could do not 0.2, yeah, 0.2 is going to go down there, okay? So that tells me, right, the fact that I can, for instance, find some constant that beyond some point x plus 1 is less than that, then we could say that x plus 1 is big O of 2x. Except not quite, right? Notice, if we say that f of n is big O of g of n, if it's the case that f of n times that constant g, right? So notice, we didn't here say big O of 2g. What we said is g itself. Okay. Now, it's probably might be a little confusing right now and all of that. So, couple of things to consider. One is, first of all, whenever we're dealing with polynomials, basically, if there is a constant on the front of that, we throw that away altogether. Okay. Now, in this case, there is no multiplying x by something, so we don't have anything there. As we talked about, this expression is dominated just by the term x, so we throw that away. Okay. And so what we would say is that linear search, our linear search function here, which, as we saw, has n plus 1 operations, this is big O of n. Okay. So that is, search is an unsorter. All right. So if I were going to kind of write this down, in big O of n time. Like so. Okay? So big O of n says that, this linear estimate is an upper bound for how this function grows. Okay? Now, can we see that sort of thing? Yeah, absolutely. And here's how we're going to do that, okay? So like I said, while we don't rely directly on timing for figuring out exactly how long something's going to take, we do for figuring out the efficiency. What we do What we do expect, though, is that, our notions of this, that is, our theoretical measures, should kind of jive with the results that we would get from looking at actual run times. Okay, so in other words, what I mean by that is if we come over here, right? So notice, at 10. Right? X is 10, Y is 10, right? If we've doubled the size of X to 20, right, then the Y value, the amount of time, is also 20. So each time we kind of increase, we see that same type of progression. Basically, if we then went to 40, again, we see that same kind of doubling. If we then went to 80, we would see that same kind of doubling. Okay, so let's see if we can get that to happen in terms of our measuring the program itself. All right. Oops. So, what I'm going to do is I'm going to actually just write some looping code here that will allow me to shall wrap it around this. I don't know, let's say 10, and then we'll say I++. Okay, and I'm basically just going to wrap that. So in other words, we do this, and then what I'm actually going to do is also each time I will set num size equal to num size. I'll be more clear. Nums size times 2. Okay, so we're going to double the number of numbers that we're searching each time. All right, and then let me actually go ahead and just kind of print out some stuff here. So I'll say, okay, let's print out the value of n, and then we'll print out time. And so here, what we'll say is we're going to print out num's size, and then that, and let's give it a try. Right, so there it is. There we start to see our times increasing as the size increases as well. Okay. Now, so I'll do a couple of things here. So let's see. So are we back in milliseconds for our timing? Let's see, I believe so. Timed search. Yeah, we are doing milliseconds, so I should probably actually change this back to milliseconds. And maybe what I'll do is at this point, since I have all these, these various ones, all this extra stuff off of there, again, I don't necessarily need that level of precision. So we'll shrink that down. Like so. What happened? Oh, this is still running. Yeah, so I'm getting to a point where my numbers are so big, this is really taking a bit too long. So I might actually want to kind of back this off a little bit. So let's do something like that, so that way I don't have to wait too long for my little tests and so forth. One, two, three, 4, 5, 6, 7. All right, so actually we'll even shrink it down a little bit more. There we go, right to there. Just so we can have some data. Now, if we take a look at the data, one of the things you'll notice is, okay, so it goes from 12 to 33, right, when it doubled, 33 to 48. So that doesn't actually look like what we would expect. Right? Doubling it, we should see a rough doubling of time. Okay, that's not quite the case. Double 12 is 24, right? This is 33. The double of that would be 66. Yeah, so it's a little weird there. Okay, let me actually add a couple of other things in here just to kind of format this nicer. Also, since we have all this stuff kind of coming out that way, what I can do is let's just use a set W of 8 and a left, and then we'll do those, and then oops, sorry. And we'll do similarly up here as well, so I'll need to break this up. Like so. All right, so that's a bit better. Probably get this even better. There we are. Okay, so now we have everything nicely lined up and so forth. All right, and again, I mean, notice it's just not quite working out the way that we would expect in terms of the notation and so forth. Okay, so what's going on? Well, basically, each time I'm really only doing a single test of the linear search, right? So, and again, because of all the stuff, all the various factors of what's going on in the system and so forth, I can get a whole host. There's a whole great degree of variability in this, right? So one way of addressing that is to basically run the test for a particular size a bunch of times. Okay, that's what I have here. Okay, so this average timed search, notice it takes a vector, it takes a number of trials that default to 10, and then it basically just runs a timed search that many times, sums up all of the times, and ultimately computes an average for us. Okay, so instead what I could do is I could basically just put average timed search here, and let's give that a shot. Okay, so 12, then it's, okay, so that's actually not too bad, right? So from 12, it should really be 24. Okay, that's kind of close, 24, so that should be about 48. Yeah, I mean, right there, we're actually getting some numbers that are fairly close. If we wanted to kind of try to force it further, what we could do is we could even add additional runs. You know, I could change this to say something like 30 or 40 or even 50, and again, see kind of how that, right, so there's 14, yeah, again, you know, so there again, sort of went off the rails. But if I continue to increase the runs, I should really get to a point where it's basically going to be running to show fairly well the type of pattern that we expect, right? So notice here, even on 50 runs, I'm actually starting to get numbers that look pretty close to where we would expect, right? So this is so the point being that our theoretical notation, right, this big O notation, does in fact bear out in the real world if we are very careful about how we do the measurements for that. All right, and yeah, you can see this is certainly taking a little longer and so forth. Again, if you run this on yours, you're probably going to get different results because different computers, you might have a faster computer than I do, you might have a slower computer than I do. Again, different numbers of programs running it at given times and so forth. All right, this video is getting kind of long, so what I'm going to do is I'm going to stop this here, and then I'll create another video to continue on talking about the different notations and looking at these issues.